Greetings and salutations. Welcome back to the Everything Astronomy Podcast. Today, we're delighted to announce that we're recording our 10th episode of Not So Sirius. And for this fitting and momentous occasion, we thought that we would choose a cool topic, galaxies. And we think there's a bunch of cool things with galaxies because not only are they cool to look at and they have cool shapes, they can tell us a lot about the universe at large, and they have there are some interesting things that are happening inside galaxies. So let's go with galaxies.
So before we can look into the cool aspects about galaxies, I think we should all have a basic understanding of how originally galaxies were discovered. So back in the 17th century, there was a French astronomer named Charles Messier, and although he didn't know what they were at the time, he was just discovering all these different types of galaxies that he classified as nebula, or just fuzzy objects in the sky. And so he discovered, 110 star clusters of these spiral nebulae, or the galaxies that he didn't know. And that was almost 300 years before astronomers figured out what galaxies were. And so after Messier discovered these initial fuzzy nebula, or spiral nebula, some people argued that they were island universes or various different things that they could be. But actually in 1920s, the famous American astronomer Edwin Hubble finally decided to measure the distance to one of these spiral nebulae. He used Cepheid variable stars, stars that are very commonly known to have a relationship between the period in which they increase and decrease in brightness and how bright it gets with luminosity. And so with these relationships, he was able to determine that the fuzzy spiral nebulae were actually way beyond the scope of our own galaxy. And so that's how the initial plots and theories that other galaxies did exist were these actual fuzzy spiral nebulae that Messier found back in the 1700s.
Hold it up. So what we're saying essentially is that when Messier first saw these galaxies, he mistook them for nebula because they looked basically the same. And it wasn't until 200 years later when Edwin Hubble figured out a new way of measuring how far objects were in the sky that we actually discovered that these objects that looked like nebula, like regular nebulae, were actually way outside the boundaries of our own galaxy.
Exactly.
And he therefore discovered that they were other galaxies in the same way that our galaxy is a galaxy.
Right, because back in the day, astronomers knew what the Milky Way was, but they kind of assumed that was the entirety of the universe. So seeing these things out in the distance, they just assumed they were in our own galaxy. But luckily, Edwin Hubble had discovered that there are other galaxies besides our own. And so when he was looking at the distances, he also decided to, plot some of the velocities of these galaxies based on the distance that he found with the Cepheid variables. And he showed that most, if not all, of the galaxies are receding or moving away from us. But he also discovered that galaxies further away were moving away from us faster than galaxies that are closer to us. And this is what was known as Hubble's Law. And this is how the Hubble's constant was formed, and the basic understanding of the large expansion of the universe.
So essentially what Hubble did, correct me if I'm wrong, is that he noticed that things further away from us were moving away from us quicker. So he thought, space must be expanding. And he realized that the further away you go has a direct impact on how fast away you're moving. And so that's how he discovered this thing called Hubble's Law. And this famous Hubble's constant, which tells us a lot, including, for example, the age of the universe, relates distance to speed in the same way that, for example, pi relates the radius of a circle to its circumference. Hubble's constant relates the speed at which space expands over a given distance.
Exactly, and this was all found on the initial discoveries that Messier found back in the 1700s for these fuzzy fuzzy stellar nebula that we now call galaxies.
And I think also it should be said that it wasn't only Hubble that should be credited for the discovery of like these distant galaxies and also the expansion of these galaxies away from our own galaxy. Like, for example, I think it was 1920, there was something known as the Great Debate, or the Curtis-Shapley debates, where these two famous astronomers debated whether, I think as Tom mentioned, we live in the Milky Way galaxy and that's the extent of our universe, or if these distant nebula, as they were called back then, are actual island universes or galaxies as we now know them. And there's a few other famous astronomers that worked at the same time as Edwin Hubble in the 1920s that came to similar discoveries.
And so I think now we should talk about what a galaxy is, because that's kind of cool. And we've started the issue. So galaxies are strange because it seems that most of the stuff in the universe is just grouped into these big blobs called galaxies. And funnily enough, then each of these galaxies are grouped into other bigger blobs called galaxy clusters, which themselves are often grouped into even bigger structures. But essentially, galaxies are just blobs or just large groupings of stars that seem to be orbiting one central kind of space called the galaxy nucleus. And then the cool thing is that these groupings of stars, and of course with the stars, that their planets and their moons and all of this, these groupings of stars in the galaxies have funny patterns. So galaxies have cool shapes, and there's multiple different kind of shapes that exist out there, and that's how we classify galaxies. So we classify galaxies off the shape or what they look like. So for example, some of them just look like a huge blob. There's just stuff all around, and those are called elliptical galaxies. And those are typically older galaxies, which means that they're forming less stars and they've been around for longer. And because they're older,
red and dead, those galaxies.
Yeah,
They're called red and dead. Yeah.
Because they're older, they have older stars and they have very little dust. And so, as Michael said, they're kind of just doing their own thing and aging away. Whereas there's other galaxies, for example, like spiral galaxies, which have these really cool arm shapes, which we'll put a picture on the screen and or links. But essentially, It just looks like someone took a piece of rope and just spun on himself, and the piece of rope is kind of making cool circular rotational pattern around.
Mm-hmm.
And these are like probably the galaxies you've seen in pictures, like when you look them up.
Yeah, like, so the Milky Way galaxy, for example, is the galaxy that we live in. It's about, I think, 200 billion stars inside of it on average. And even though you can't really see the structure of it, scientists over the past, 50 years have been able to piece together using different telescope surveys. The most recent one being the Gaia Space Telescope that's been able to pinpoint exact locations of stars. And they've been able to kind of figure out what a galaxy looks like from the inside, which is really hard to do. And we've come to the conclusions that it is a spiral galaxy. And also our nearest neighbor is the Andromeda Galaxy. And I think that's probably, besides seeing drawings of the Milky Way galaxy, that's probably the most recognized galaxy. And the Andromeda Galaxy is also a spiral galaxy, and it's a bit more massive than our own Milky Way.
The other cool thing with this Gaia Sky Survey, so there's this telescope that's orbiting Earth, and it's mapping with a higher degree of precision than we've had before, both where stars are and where they're moving and how fast they're moving. And that's allowing us to complete essentially a much better picture of what the Milky Way looks like, because we're inside the Milky Way, so it's really hard to see. It's really hard to get a bird's eye view.
Yeah, you can't really
from
take a
inside
stick
from within. Exactly, you can't just you can't just build a tower and see from above.
Right.
And so, essentially, the way that we're going about trying to figure out what the Milky Way looks like is we're going to try to find or map as many stars as possible and where they're going. And with that data, we can then kind of reconstruct what the Milky Way looks like from inside. So that's
like the
cool.
reason why, it is called a spiral galaxy, as Joe said, because they have these arms, but if you look at the direction and trajectory of these arms, they're like circling each other almost. And so if you were to take a pencil and draw a spiral out, you kind of get an idea of how these arms or the directions they're going in, which is kind of interesting. Why they seem so cool and so different.
And then the arms bring up I think one of the coolest features of galaxies is the reason why we have these arms, essentially, because Newton's laws of gravity figured out that the further away an object is, the longer it takes to orbit if it's orbiting in a circle. For example, we on Earth are orbiting the sun, and that takes a year. It takes us a year to go around, but Jupiter takes like something like 60 years to go around, right?
Exactly.
And then Neptune and Co take even longer.
Yeah, it's like 200.
Yeah, and so the funny thing is, imagine that we were, all of the planets were in a straight line and were going around the circle, or around the sun in a circle.
At the same speed, yeah.
Very quickly, you would find that because because the Earth is going much faster than the planets further out, the initial straight line gets broken up, and then you have just a random pattern. And so, that would lead that's not consistent with there being a real spiral structure. Or, if there were spiral structures, it would be an accident more than the result of a physical process. But because we see so many spiral structures, in fact, a large portion of galaxies are spiral, and most galaxies that are not within galaxy clusters, which we'll get to in a while, are actually spiral galaxies. So that tells us obviously that there's a thing that's driving these spiral shapes. And so there's a couple different ideas about what it is exactly that makes these spiral structures. Because, for example, a good analogy would be if you have a bunch of cars driving around in a circle, the cars outside have to go further, and so you're not going to be able to maintain a cool shape for a long time. And so
you're not just getting really twisted.
Right.
And then it would stop looking like anything very quickly. And if you had billions and billions of cars all going at different speeds, then it would just really look like nothing. It would just be a mess of stuff. Yeah. And so one idea was that, is this idea of a density wave. And so, if you will, and the density wave, I'll get to the maths in a second, but it's this cool idea that the spiral arms are not actually, the entire arm is not moving. It's more like a wave of material moving out, spinning around. In the same way that, for example, if I take a cork or something and I put it in water, if I make waves in the water, the cork doesn't move. It doesn't move sideways. It just goes up and down.
Right.
Maybe, and it seems that the mechanism through which these arms arises is not actually that the stuff is moving around the galaxy in a spiral shape. It's just that this is a wave, if you will, that's bunching all of these planets and stars together, and it's the wave that transmits and that goes around.
It's almost like a temporary traffic jam where like cars are trying to get past each other, but they come across this density wave.
Yeah, it's like if you're on the highway and you hit like a really bad traffic jam. If you get stuck in it, it doesn't mean you're not moving forward still. It just means you're all stuck together. Like behind you is moving perfectly fine, in front of you is fine, but you're stuck in that slower pocket.
And the other cool thing with this quote unquote stellar traffic jam is that in a traffic jam, there's more people closer together. And with stars and dust and all of the stuff that you find in a galaxy, that actually leads to much more star formation, because higher density areas are more likely to kind of spur on star formation. So within these sort of denser areas, you have more stars forming, which again contributes to there being more a brighter arm. And then the other thing again is that the more stuff there is, the higher the gravity. Exactly. So actually the arms pull stuff in as well. And all of these things combined, you have an arm, which is cool.
And then when you look at like Hubble Space Telescope images, you can see the spiral structure. But then if you take a similar telescope, the Spitzer Space Telescope that looks in the infrared, you can look at those same spirals, but you see these really, really bright spots along I think it's the inside part of the arm. And that's where, as Joe was explaining, that's where all the stars generally form in galaxies, is along the spirals, because of all like the compression, the heating up.
And so like we kind of consider spiral galaxies to be younger almost because there's so much star formation in these arms that are going on. Which is like, as Joe mentioned, why these stars are so much brighter. And also it shows why we see it so much more common, why we see spirals so much more common, because if you look at elliptical galaxies, they're pretty dim. And so if anything, they're harder to see out in space. Whereas spirals are so bright that we can like track them pretty exactly almost, where you can see the light coming from them. Whereas ellipticals, like we have an idea of how many there are in the universe, but they're hard to see just because they are older. They're less bright, and there's not as much star formation or anything like that going on.
With the theories of spiral galaxies being younger and elliptical galaxies being slightly older, it's made this very interesting, development, how elliptical galaxies could have been formed, whether or not spiral galaxies, collide with one another and the angular momentum cancels, and that's how you just get massive conglomerates of really, really old stars, because the spiral galaxies have burned through most of their dust, and that's why you don't see a lot of dust in these elliptical galaxies anymore with no spin.
Yeah, because it used to be thought, I think, by Hubble and his contemporaries, that you had that elliptical galaxies, so the galaxies that don't really look like much, used to then evolve and form and turn into spiral galaxies, right? Mm-hmm. Whereas now, with the development of telescopes that allowed us to see in other wavelengths, we've been able to determine that, in fact, the elliptical galaxies are the older one with little star formation. So it makes very little sense that you would go from an old, not star forming region to a young star forming region. In fact, that doesn't make sense at all. Yeah. Right. So we thought, it's probably the other way around. And in fact, given that elliptical galaxies are much older than the spiral galaxies, it's probably the case that spiral galaxies, when they collide into each other and all of this good stuff, they then form bigger galaxies that become elliptical galaxies.
Right. I do also think it's worth to mention, though, that all this galaxy formation, we have a general idea of what might happen, but there are different theories that cause, that there are different theories out there that for why ellipticals will form and why spiral galaxies form. Like, for one example, I think I was reading where, people think that elliptical galaxies might form out of spiral galaxies colliding with each other. And that, like Tom said, the angular momentum cancels out wherever, and then you're left with elliptical galaxies, which is why they also seem older, because in those collisions of spiral galaxies, these stars the dust and the gas will heat up, and there'll be one giant moment of stellar formation. And after that, they're not rotating anymore, so nothing really happens, which is why you're left with these older stars in elliptical galaxies. So
there's another cool thing that Gaia actually, so this satellite that we talked about earlier that's trying to map the Milky Way. By the way, Gaia was launched in 2013, so it's not exceedingly old as far as science goes. And Gaia discovered, I think fairly recently, that maybe the solar system, so our solar system, was the result of a collision between our galaxy, the Milky Way, and a smaller dwarf galaxy called Pegasus, I think. And because, our galaxy, the Milky Way, is 10 billion years old.
Right.
But our solar system is only 4 billion years old or so, which is interesting because you would think that by the time a galaxy is 6 billion years old, and we know this, galaxies that are 6 billion years old tend to be more settled, older. They're less young galaxies. So the star formation is less likely to happen in older galaxies. Right. And the interesting thing is that it seems that actually 5 or 6 billion years ago, this smaller dwarf galaxy, Pegasus, collided with the Milky Way galaxy a first time. And actually, it's thought that it might have collided it collided twice, because it hit one edge of the Milky Way galaxy and the gravity kind of flung it around, and it hit the Milky Way galaxy again. And now I don't know where it is. I didn't read that far. Oh, I should have.
Right.
But that's an interesting. The galaxy collisions are interesting, and actually, that is not the only time that the Milky Way galaxy will or has collided with another galaxy. Given that in a bunch of billion years, I don't remember how many, a couple, I think.
Yeah,
5 billion years, the Milky Way is going to collide with our nearest neighbor, the Andromeda Galaxy, which is 2.5 million light years away. And the cool thing as well with galaxy collisions is that not that much happens. If I take two trains and smack them into each other, a lot of stuff happens. You can clearly tell that there's damage. But because galaxies are so big and there's so much empty space between them, actually most stars and most planets will never collide with something else. So all you have, well, I mean, it could happen. We might get
Right.
hit by something,
Yeah.
but it's very unlikely. I think only a couple % of stars will end up colliding with other
I think the
stars.
statistic is that if you put 3 honeybees in the continental U.S. and have them fly around, there's a higher probability that those 3 bees will collide into each other in the U.S. than a star within the Andromeda Milky Way colliding into each other.
And that seems hard to believe because like these galaxies, when you look at the pictures of them, at least they seem so large and they seem so full. But you have to understand here that like these are pictures that we're taking, and so there's a lot of dust that you're not seeing. There's a lot of space that we can't see up close, and so as big as they are and as how much dust there is, there's a good chance nothing will get hit.
But also on
Right.
the smaller scale, you won't see many collisions. But if you're looking out at, like, say, in another galaxy, looking upon the Andromeda and Milky Way approaching each other, then it will be quite a spectacular view. But it should be mentioned that these occur over very, very long periods of time. So this won't even occur until 5 billion years from now. But also, when the Milky Way comes and the Andromeda come together, it just doesn't collide all at once. They have to like kind of sideswipe each other, then pass back through. Then also
Right.
it matters like the difference in mass between the 2 galaxies. And so for, as Joe was talking about before, with this so-called Pegasus galaxy, this dwarf galaxy or satellite galaxy that passed through the Milky Way in the past, that got shredded to pieces in a sense because it was so small compared to the massive Milky Way galaxy.
Right. It just became a part of the Milky Way. I'm sure it knocked some orbits like loose, and some solar systems and stars got ejected. But in the end of the day, they just kind of merge into one. It's like
And
if you take a tank of red water and a tank of blue water and you splash them together, sure, there's going to be some droplets that escape the container, but for the most part, it just meshes into one purple thing of water.
And then the one weird thing about this so-called Pegasus and the Gaia being able to look and figure out that it may have collided in the past however many billion years is like, how do astronomers figure that out? Because we take a telescope in 2013 and we take a snapshot in different parts of the night sky, yet we can figure out that there was something there a really long time ago. And the way they're able to do this is basically look through the data and look at patterns. And these patterns are called tidal streams, or these collections of stars that kind of stand out from all of the other Milky Way galaxy stars. And they also look specifically for stars of the same age. And so as this dwarf galaxy or satellite galaxy passed through the Milky Way galaxy in the past, it may have ignited star formation. And so they can look at star formation that occurred at a certain time, and that may indicate when this galaxy initially passed through. And then if you look up like Sloan Digital Sky Survey online, and then Sloan Digital Sky Survey tidal streams, it has this really cool image of all the tidal streams that we've discovered so far in the Milky Way galaxy. And there's at least 10 that like these really defined patterns, these really extended streaks that go through the Milky Way galaxy. And that's what the Gaia Space Telescope, at least one part of it, looks at. And so basically you're looking at past snapshots of what the Milky Way galaxy looked like.
Yeah, well, and I mean that's interesting because I think we've already talked about it, but Lagrange, the famous French mathematician, physicist guy, he had this idea like 300 or 400 years ago when he was developing mechanics and so how things move. He had this idea that if you knew everything about how things were moving in the present, you can know everything about how things would happen in the past and the future, which is kind of true, I guess. If I take 3 tennis balls and I throw them in the air, if I can measure their speed at one point, I can know where they're going to go, and I can also know what happened to them a little bit before I threw, how the balls were in my hand before I threw them.
The direction in which they were thrown, and then at what speed. Yeah.
And so obviously that's a huge philosophical, physical question that brings into play many things. But it is interesting that in this case, just by measuring the kind of the state of the present, we can know both the future and the past of how these stars are going and where they were.
Yeah, and that's true. And I think a misconception about astronomy is that it's very observational based, where people are looking through telescopes or using these large surveys. But also the other half of astronomy is simulations and more theoretical astronomy. And so that has to do with, like, simulations are very popular in galaxy research because if scientists or astronomers now know what the current conditions of a galaxy are, and they can look at snapshots of different galaxies at perhaps similar stages but at different times, they're able to kind of piece everything together and run a simulation and see how that matches with what our observations say. And so in a sense, we are getting closer and closer to being able to kind of replicate the history of certain galaxy groups.
It's like the same idea of throwing a tennis ball in the air. You can kind of map out where it's going to be, where it's going to land. And so it's the same idea with the galaxies, where you know where it is at a certain point, and so because of that, you can predict where it's going to go eventually, or what's going to happen.
Yeah, just a bit
I
more
also
complicated.
think, yeah, just a little bit more complicated, a little more math and science. I also think another thing worth mentioning, though, is that when we often look at these pictures of galaxies, we'll see something at the center. So like Milky Way, for example, you'll see a circle, right? And you'll see that everything usually orbits around. You'll see the arms that are spinning around the center. Even in elliptical galaxies, these blobs that look like eggs, you'll still see something in the center. And I think it's worth mentioning that, I think we theorize that like there are black holes at the center of these galaxies, like supermassive black holes that are basically their gravity is holding everything together in a sense, which is why I believe, correct me if I'm wrong, you don't see these galaxies or all this dust dispersing basically, because essentially gravity is all holding it together.
Yeah,
like
the bulge in the nucleus is just the gravitational, it's so strong, like nothing can really escape. And that's why in like when you look at pictures in the center, it just seems like one mass star, just bright luminous objects.
Yeah, and the galaxies, as we mentioned, I think in the introduction, they're cool because they can teach us a lot about how the universe was very early on, and what was it like just that kind of just after the Big Bang. And so one of these really cool questions that arises is, what the hell happens with the black hole at the center of galaxies? Because on the one hand, black holes are really heavy and they have very strong gravity, so it makes sense that things would get attracted to kind of in the direction of black holes and start spinning around them.
Exactly.
And so in some sense, I guess you could say that black holes can be kind of a cosmic glue, if you will. They stick things, and as the nuclei of galaxies are moving around, they will collect more stuff. But then there's this weird thing where these black holes at the center of galaxies are huge. They're millions, if not billions of times heavier than most stars are. And as we talked about in our previous black holes episode, please check it out. We thought it was pretty good. That that black holes, as we theorize them, most commonly arise out of stars collapsing on themselves. But then it doesn't make sense that black holes can be so much bigger than stars, because you can't make something out of nothing. And so there's kind of two mechanisms that could allow huge black holes to happen. Either you have lots of stars collapsing in close proximity, and so all of these black holes are merging together and essentially cannibalizing each other, forming a bigger and bigger black hole as you're going along, kind of like a snowball effect. Or on the other hand, you could have kind of a very dense, dusty environment without stars yet, that instead of forming stars might form a black hole straight away, where I think the dust would collapse in on itself and form a huge black hole. And so the question is, and I think, and I can't be entirely sure about this, as modern astronomy is a pretty complex subject, but I think a big open question in modern day astronomy is, which came first, the chicken or the egg, the black hole or the galaxy?
Exactly, the chicken or egg kind of type question. Because we have to realize that these galaxies are also formed from, like, we think, large clouds of dust and stellar clouds. So, like, is a black hole forming at the same rate as galaxies forming? Everything just shapes around it, or like what kind of comes first? We don't really know. Which is pretty cool to think about. Or is it just that as the galaxy is forming, everything just comes to the center, and that naturally just forms a black? Like we just don't know.
Yeah, and it seems, although I think there are some exceptions, that most large galaxies have a supermassive black hole at their center. But then, as we will talk about right now, I think there's lots of other types of galaxies that are not huge and that are not super big. There's dwarf galaxies, there's irregular galaxies, there are ring galaxies, there are nucleus galaxies. There's tons more, I think.
There's satellite galaxies.
Satellite galaxies, quasars, Blazars?
Blazars?
Blazars.
And Mazars. I think that's a word.
Yeah,
there's tons of other kinds of galaxies.
But all under the same idea of just a collection of a bunch of stars.
Exactly.
Right.
And
like don't get them like wrong. Like they're still massive, just not in comparison to like normal spiral or elliptical or
You have to think
other
in terms of
galaxies.
astronomical numbers, where it's like,
Right.
things are really big if they're really, really big in terms of our like our regular chart numbers, or they're really small and they're still really big. Quasars not as big as those other big things.
It's like how, from our perspective, the sun is massive, but it's puny compared to any other star you could possibly find.
That's average.
Well, it's average.
Yeah, you know what I mean, though. Like, there's bigger and smaller, and they're still large, but in comparison to everything else,
Anywho's, one really cool type of galaxies is the quasar, which stands for quasi-stellar radio signal.
Sources, I think. Source?
Quasi-stellar object preview. Wait, hold up. I have
Anywho's. It's a
Cool.
quasi-stellar kind of thing.
Quasi-stellar object, abbreviated QSO.
No, that's not it. But anyways, quasars, QUASAR, are these galaxies that emit a lot of radio waves.
Mhm.
By a lot, I mean like millions of times more than most
They're
other
pretty
galaxies.
Like enough to
pretty
like
unstable,
burn.
isn't it?
Yeah.
And the cool thing with quasars is that it was noticed that the two things were noticed, essentially, that the radio waves follow a power law, which is not super interesting. But the cooler thing is that all of the radio waves were polarized, which means that, if you will, waves oscillate up and down, and they can oscillate in any number of directions. So most light beams that you see are not polarized. And so the way you have waves that are oscillating up and down in this direction, up and down in all sorts of directions. And for example, you can buy polarized sunglasses, though, which only let in light that's oscillating in one particular direction.
Right.
And for example, light that reflects off water gets polarized, which is why sailors and people who do stuff by the sea often have polarized, or should have polarized glasses, because it can cancel out reflections better.
Right.
But it was noticed that radio waves that come from these quasars, which are galaxies as well, are polarized, which is telling us that, which is another thing, which is one element that points towards the fact that the process through which these radio waves are being emitted is called synchrotron radiation, which is a phenomena that arises when high energy charged particles are moving are being radially accelerated or in a magnetic field. And so which is cool. And one of the mechanisms through which we think this happens is the black hole accretes material, and which means that stuff is spinning around the black hole. And as the stuff is spinning around, there are charged particles spinning around. And if there's a high magnetic field, they'll start to emit radio waves, or waves in general, but radio waves particularly in this case.
High magnetic field can come from like very, very strong magnetic fields, typically come from supermassive black holes with very, very high rates of rotation.
And so then you have radiation being shot out from kind of the plane of the galaxy out. In fact, you have, in some galaxies, we've noticed that materials seem that the kind of the jets leaving the sides of the galaxies are moving faster than the speed of light. Now, as we know, that's impossible. And it only seems that they're doing that because of relativistic effects. But nonetheless, it's still cool because it's telling us that stuff is being emitted really quite fast. Right. And the cool thing with these quasars is that we know from the light that gets to us that they're really, really far away. And things that are really, really far away in the universe are really, really old. And that's the case because if it takes 10 billion years, say, for the light from that object to reach us, we know that that object is at least 10 billion years old, which means that it's pretty old on the scale of the universe. And so that kind of is an important piece in the puzzle of solving where and how and when did galaxies form. And so what it's telling us, what quasars seem to be pointing towards, is that supermassive black holes formed pretty early on in the scale of the universe, and maybe it's from these supermassive black holes that you then start to build up these bigger, more complex galaxies, the spiral or the ellipticals.
Mm-hmm.
I also think it's worth to mention that we used to think that quasars were indications of alien life because of the
Right.
amount of energy that was coming from them that we could detect. We were like, this can't be some source from anything.
Yeah.
natural.
It's a ridiculous.
That's always the go-to excuse for an
Right.
astronomy when we can't figure something out.
There's no way it's possible. It's impossible.
Yeah, a lot of discoveries in astronomy too is they've discovered something that they think is physically impossible, and so they study it more, and then that's how we learn about these super cool objects.
Exactly.
Well, and there are, I think they're called pulsars, but the mechanism is the same. Whenever you have these big jets, they have a pretty specific orientation in space, and when the jet. And so if, for example, the object is spinning in some way, the jet is spinning with the object too. And if the kind of jet smacks us and hits us, we see light of some kind, or our telescopes will detect something.
Right.
And because they're spinning, and usually they spin at a constant speed, that means that the light will hit us at a set frequency. And there's been, I think, quite a few of these in sort of modern astronomical history where we've just seen light shine at us for, I don't know, 10 minutes, one day, half a day, and it comes back every couple of days, every couple of hours. Sometimes it comes back every couple of years. But many people have used that as evidence for aliens, or have said, oh no, there must be aliens because we're getting beamed by these things at a set frequency. Of course, we know better now.
Right.
But that's still kind of cool.
Mm-hmm. Yeah, but with these, these quasi early galaxies like quasars or different types of galaxies, I think it's also important to bring up the smaller galaxies that are more established, like dwarf and satellite galaxies. As we mentioned earlier, I think you said it was called Pegasus. I crashed in the Milky Way, but the Milky Way also has some very famous satellite galaxies like the Magellan Clouds, right?
Magellanic. So if you're on the southern hemisphere, you're probably familiar with the small and large Magellanic Clouds.
Yeah, but studying interactions with these satellite galaxies also give us a lot of information for spiral and elliptical galaxies as well.
I mean, they're also called satellite galaxies because they're just smaller galaxies that are orbiting around larger galaxies. It's kind of like, our solar system where we have the sun and these planets orbiting. It's like there's a large galaxy and there's these smaller galaxies orbiting around. So it kind of just goes to show that there's a lot of stuff in space that we just characterized there. If they contain stars that are galaxies, and they're all really cool, but there are a lot of them to go through.
And one thing that I don't actually know the answer to, but I think would be interesting, is how much material lives outside of galaxies, because galaxies are groupings of stars, if you will, but even between the stars that are within one same galaxy, there's an incredibly large amount of quote unquote empty space. So if the space between galaxies is a lot emptier, I wonder how many stars just happen to form outside of galaxies, or is that even possible? That's something I don't have the answer to at all. But I think that's a very interesting question.
It really comes down to a question of like how many objects are there in space in general, because everything kind of works around gravity, right? So even if you have dust and you have an object, it'll be attracted to it because of its gravity.
Right.
So
Well,
it comes to a question of like, there's dust in empty space, but is that how ionized is that dust? How many rich materials are in the dust that can allow things like this to occur?
So. Yeah, because I know in the search for dark matter, I know there's a lot of simulations that are going on and theories that they're trying to prove with the simulations that say, dark matter, dark energy kind of like form in webs and have different densities in the universe. And so maybe, the dark matter between galaxies isn't as dense. And so that's why there's less objects, but that doesn't mean there's not, matter there that we can't see it's something we just have to look into.
Yeah, the hot word nowadays in astronomy, at least in our department here at Michigan, is dark matter halos. And so looking at images of galaxies, they look quite large, except the extent and the gravitational mass extent of those galaxies extends much, much further. So for example, what's called the dark matter halo of the Milky Way galaxy nearly extends to and overlaps with the dark matter halo of the Andromeda galaxy. And so once you leave the visible stellar component of galaxies, it doesn't mean you have left the entire galaxy. You're still in a region with a lot of mass and gravity.
Right. Yeah, I
Just
think
don't
we had
know what it
mentioned
is.
it. We had mentioned it in a previous episode of Not So Serious, I think.
Check it out; it's pretty good as well.
Yeah,
Although I
they were
say so myself.
they were studying the rotation curves of galaxies, and they found that far beyond the edge of the galaxy, there wasn't a decrease in the velocity or the mass that we could see beyond the edge of the spirals. And so that's kind of where these dark matter halo theories came up, where the dark matter is accounting for the missing matter that causes galaxies to form, but then these interactions that we can't see are also affecting how galaxies interact with one another, and that's another reason why we kind of look into dark matter.
And one of the truly cool things with galaxies is that they teach us so much about how the universe started and what the universe is all about. Because it's, for example, galaxies are really the first thing that kind of got us onto the dark matter train. We noticed dark matter by observing galaxies.
Right. Yeah, with Hubble's constant, that's how dark energy was theorized.
Yeah, exactly. And we see so many things with galaxies. For example, with the Hubble Deep Field, which I think is probably one of the most famous pictures ever taken in astronomy, where the Hubble Space Telescope was pointed at a region of seemingly somewhat empty space. And instead of seeing nothing, we just saw thousands of galaxies, just an incredible number of galaxies, which tells us that the universe is not only full of these galaxies, but it also it tells us how galaxies are distributed in the universe. It tells us about more. It's proof, again, that general relativity is a real thing. It's proof of so many things and is the kind of question book for so many things.
One of my favorite things.
Oh, sorry, go ahead.
No, I was gonna say one of my favorite things about looking at galaxies is that looking at new images of galaxies never gets old. Like as Joe said, looking at the Hubble Deep Field or the Ultra Deep Field, there are thousands upon thousands of galaxies, and yet every single one is quite distinct from one another. And so, of course, we have what we're used to being the Milky Way galaxy, a spiral galaxy, and perhaps if you've seen images of elliptical galaxies. But I could just scroll through archives of Hubble's images of galaxies. And for example, one of my favorite ones is Hoag's object, which is called the Ring Galaxy, and it's literally if you on your phone, I'm assuming if you're listening to this, or your computer,
I can put an image up
it's
too.
just this ring, and then in the center is the core of the galaxy. And I have no idea how exactly it formed, but it's like it doesn't even look like a galaxy. It's amazing. And also, as Joe was mentioning, like studying these galaxies tells us so much about like where our universe was, where it is now, and where it's headed in the future.
And another cool question is, we know that there's stuff that is smaller than the atom. We know that there's the atom. We know that there's molecules. We know that there's planets, solar systems, stars. We know that there's galaxies. We know kind of the subgrouping of sizes of everything. And when we get to galaxies, one might naively think that that's the end. Galaxies are the biggest thing. But we know that there's clusters of galaxies, that galaxies group and band together. And they themselves form clusters of things. And it's thought that there might be clusters of clusters, I think.
Super clusters.
Yeah, super clusters. And I think it even goes like hyper clusters and then cluster complexes and
either way. But then I think from the supercluster onwards, we get to sizes that are significant within the size of the overall universe, which is an interesting thing because we know kind of from theoretical calculations how big the universe is, but we're never really close to being able to determine how things are on the largest structure of the universe. And so with galaxies, we can kind of start to study it more. We can start to study the distribution of these galaxies. We can start to find and discover patterns in the overall structure of the universe, which is cool and interesting. And will hopefully teach us a lot about the world.
I also think it goes to show that there's still a lot to be done with galaxy research.
Yeah, for sure.
It could even be that the classifications we have now could change in the next like 50 or 100 years, where we learn more about these smaller galaxies and can categorize them differently, where they're not necessarily galaxies and be different. So I think it kind of goes to show that there's a lot to be learned here. I think more importantly, there's a lot of research still going on. So I know Michael has been doing some research at the university with a professor. And so maybe you could briefly share, but there's also like just I think a lot of other research that if you have a chance you should go look, and I think we'll cover a bit here.
Yeah. So in terms of
there's just a lot going on.
in terms of galaxy research, we're definitely wading our feet in the ocean of galaxy knowledge. Like it's only been the past not even 100 years that we've known that galaxies exist, and so I imagine in the coming decade and 2 decades with the launch of the James Webb Space Telescope, and then there's another one that slipped my memory right now. I can't remember, but like all looking at galaxies with high resolution, better technology than ever before. So I'm excited. Like even though we don't probably know much about galaxies, I feel like we do, but we probably don't. It's exciting with like knowing that these are advances are going to be launched, and we're going to have the opportunity to learn more and more. But as Sam said, yeah, I work with a professor at the University of Michigan, and I look at galaxies. And so we mentioned briefly spiral galaxies and elliptical galaxies and how often they interact with each other gravitationally. And so I look at, if you're in the northern hemisphere and you know where Ursa Major is, the galaxy group I look at, which a group just means that there's, in this case, there are 3 galaxies that are relatively close to each other. It's, I think, somewhere in Ursa Major by the North Star, or not the North Star, that's Ursa Minor, somewhere up north. Anyway, so these 3 galaxies are gravitationally interacting with each other, and my professor wrote a proposal, maybe in 2015, I think it was, to take time, which is the equivalent to only like 3 hours of telescope time, using a telescope out in Hawaii known as the Subaru Space Telescope. It's actually owned and operated by the Japanese Space Agency, but for some reason they're able to exchange time with us in the US. And we used this telescope, looked at it in, for the most part, the visible part of the spectrum. And through that, we're able to not only image the galaxies, but attempt to resolve individual stars. And so one thing I didn't realize before doing research with this professor is that we have no idea. We know what these galaxies look like that are very far away from us outside of the Milky Way galaxy, but we actually have no idea what the individual stars look like. And we barely know, despite with Gaia, we barely know what the individual stars look like in our own Milky Way galaxy. And so this telescope is it's very powerful. It's able to resolve approximately individual stars in this distant galaxy known as the M81 group. And we're able to, what I do is I look at interactions between these 3 galaxies using those stars. And so I look anywhere from stars 25 that were formed about 25 million years ago in this galaxy group up to 300 million years ago. And I'm able to use this stellar group, or these group of stars known as red helium burning stars, meaning they burn helium at their core. And what's interesting about these stars in particular is that there's a 1-to-1 relationship between where they fall on a very famous, if you've ever taken an introductory astronomy class, known as an HR diagram, or Hertzsprung-Russell diagram, I think it's called.
Yeah.
That compares the temperature of a star and its luminosity or its brightness. And there's a 1-to-1 relationship between where it falls vertically on the HR diagram and its age. And that's not the case with any other star group. So main sequence stars kind of overlap with each other. Red giant branch stars overlap with each other. So even though we're able to resolve and figure out that these are main sequence stars and these are red giant branch stars, we're not able to know exactly what their age is. But we can with red helium burning stars. And so with my research, I've been able to vertically select different age stars and kind of run the clock forwards in time. So I'm able to select stars very low on the HR diagram that are red helium burning stars and look at what this galaxy group looked 300 million years ago, and able to take a selection of stars just above it and above it and above it and above it, and almost create a GIF or a GIF, however you pronounce it, of what these stars look like 300 million years ago up to 25 million years ago. And you can basically use these red helium burning stars as a tracer star of how this galaxy group has evolved over the past hundreds of millions of years. So that's what I do in a nutshell. But there's a lot of research, not only at this university, but at all universities. Galaxy evolution, galaxy structure is still and will be in the future a very hot topic, because there's so much to that we don't know yet.
Cool. And yeah, so galaxies are cool, galaxies are useful, galaxies are interesting, And we hope that this topic was a fitting 10th episode of Not So Sirius. Thank you for watching as always.
See ya.
Hey everyone, thank you for listening to this podcast episode. This is Michael.
This is Sam.
This is Tommy.
And this is Joe.
If you're listening to this on YouTube, make sure to like, subscribe, and share with your friends. And if you're listening on Apple Podcasts or Spotify, make sure to leave a review. All of the show notes can be found either in the description below or on our website. Thank you again for listening, and we'll see you next week with more Everything Astronomy.